Okay, so today's lecture we will be talking about state machine synthesis. We will initially start talking about the equivalence of Mealy and Moore machines, how we can transform a Mealy machine to a Moore machine and vice versa. Which the machines are equivalent with a very small difference, we will see that, and later on we will see all the steps that are involved in synthesizing a state machine starting from its specification, which is the state diagram. So, first we talk about the Mealy and Moore. So, in terms of Mealy and Moore, there is a very simple transformation that is possible. If you want to transform a Mealy machine to a Moore machine, for every state with distinct outputs on incident edges. So, if you consider a state, there are number of edges which are incident to it. All those edges which terminate on that state are called incident edges. So, if you have multiple incident edges, then you look at what are the outputs that are associated with those incident edges. If multiple outputs are associated with those incident edges, then that particular state gets split into multiple states. If all incident edges have the same output associated, then that particular state does not split and it gets associated with that particular output. But if there are multiple outputs for the incident edges, then you split it into that many number of states as there are outputs and associate the edge output with the state. After all, one major difference between the way we look at the Mealy and the Moore is in case of the Moore machine, the outputs are associated with the states, and in case of the Mealy machine, the outputs are associated with the transitions. So, we associate the edge output with the state. Of course, we have to redirect the edges appropriately, and because we are also creating new states, we will also might be required to have new edges for those states, but they will be very automatically clear that how those they will be very simply clear that how those edges are need to be generated. Define the new edges from the split states as per the original Mealy machine. So, we will see a simple example of this before proceeding with the rest of the synthesis process. So, let us look at this particular diagram. It is the same old design that we had for the parity generator or for the odd or even, which checks whether the number of ones are odd or even. So, we had two states S0 and S1, and S0 is if the number of ones were even, and with a 0 it remains there, but once we get a 1 we go to 1 with an output of 1, and similarly this is number of states are odd, and this keeps on remaining here if the number of we keep on receiving zeros, and once we receive 1 we go over here, but with this 0 the output is 1 and with this 1 the output is 0. So, state S0 corresponds to number of ones being till now received being even, and this corresponds to number of ones received being odd. Now, if I look at it, if I look at this state S0, there are two edges which are incident on it. The two edges that are incident are this particular edge and this particular edge, and I look at the outputs that are associated with these two edges. The output that are associated are zeros, both the outputs are same. Implication is this particular state will not split, because if the outputs that are associated were different with these two edges, then this particular state would have split into two different states, one for each of the outputs. But in this case, because both the outputs are same, so I do not split, but of course I define this state to be a new state S00. Okay, this is that S0 state with 0 output, and I call it S00. The output I associate with it is 0. This is of course just the name of the state, and this is the output that is associated with it. Now, if I look at the other state, which is S1, S1 has two edges which are incident on it, and both these edges happen to have the same output. So, this is an example. So, in this case what happens is S11 will be, the state S1 will not split, there will be only one state corresponding to that in the Moore model, and that will be called S11, and output that we associate with it is 1, that was the output that was with the edges. As far as the transitions are concerned, there is really no change over here, because actually no new states were created. Because no new states were created, I have the same transition. So, 0 will keep on taking you there, and 1 will take you from S00 to S11, because S00 is equivalent of S0 and S11 is equivalent of S1. Rename because I am calling it a Moore machine, so I have different names. This S00 is just a name, I can have alpha and beta or A and B, it does not really matter. Okay. So, that is completely because in theory I can have, we will also take another simple example, we will see that the number of states could even increase. So, when the number of states increases, they cannot decrease. Okay. If this is a minimized Mealy machine, I cannot have a fewer number of states in the Moore machine, I can only have larger number of states, because at each state which has incident edges with multiple outputs gets split into multiple states. In this case, it so happens that both the states have, all the incident edges have the same output, and because they have the same output, I do not split. We should typically rename them, we should not call, because they are actually different states. And we will also like to now look at, though we are calling them equivalent, but we are calling them equivalent little loosely, and I will define why we are calling it little loosely, because there is a difference, and the difference comes out if I look at the waveforms. So, what I have over here is, let me start from this. So, I have a clock waveform. So, this is basically showing that just a running clock. So, I just taken a duty cycle ratio of 50%, like half 50% time on and 50% time off, it does not really matter. What I am really interested in is these rising edges. I am assuming that after all, that state register that we have mentioned transforms the next state to the present state, and let us say those things are happening at the rising edge. And I am also assuming for this particular discussion that my inputs are synchronized, that is, inputs also change, but the inputs change after this edge. So, that is, for the input for this particular state that comes will be the input that comes just after this and remains up to this particular edge. So, now this is my input. So, if I now consider, so these are the periods. So, let us say this is my period T1, this is T2, these are the clock periods T3, T4, T5. I have some 5 clock periods that I have considered. So, if I consider in the first clock period, my input is 1, in this my input is 0, my input is 0 here, input is 1, and again input is 0. So, this is a sequence of 5 inputs that I have. Now, if I look at my Mealy machine, how will the Mealy machine proceed? So, the machine is the same, please remember what I had discussed before. So, it is easy to remember this machine, that is why I am not showing it over here, but now you can see that what happens. I am starting with some state S0. So, before this clock was applied, I was in my initial state S0, before the input was applied, I was in my initial state S0. I will actually, the input appears after this clock period and the input is 1. I will actually make a transition to state S1 over here. But with the state S0, I am in state S0 and my input is 1, my output will actually be 1, because this is what this Mealy machine defined. If S0 and input is 1, my output is going to be 1, and because I am on this particular transition arc, so I am going to have an output of 1. The actual transition to state S1 will only occur in the next clock period, because the present state will become the next state, remember, next state will become the present state, and at the edge this particular activity takes place, and so I have S1 over here. Now, I am in state S1 and my input is 0, so I will continue to have my output 1. So, this is actually the output Y, this is also the output Y. So, I will continue to have output 1, input is 0, I will continue to have output 1. Now, in this case, I will go to state S1, remain in state S1 till this particular time, but my output will go to 0, because state S1 and input 1, I am going to be on this particular arc. So, my this one will become 0, and of course, I will make a transition to state S0 with this, and of course, my input is 0 and I am in state S0, so my output will also be 0, and this will be the waveform that I will generate. If I now look at what the Moore machine waveform, the Moore machine generates. Moore machine actually again is going to perform the state transition only with the same clock edge. This is the assumption we are making, except that it will continue to, though the input is 1, it will actually, because it is in state S00, output is essentially associated with the state and not with the present state and the input. So, it will remain in the output will be 0 for this particular period. Now, once the input actually is sensed over here, so I make a transition to S11 and my output will be 1, my output again will be 1, my output again will be 1, and then when I actually get sense this S11 and this particular 0 will make a transition to S00. So, now what we see is, so it is not very difficult to see from this that any waveform, of course I only drawn it for 5 clock cycles, I can draw it for 100 clock cycles. This particular waveform, that is Moore's waveform, will be just be 1 clock shifted from this particular waveform. The output, not I am not talking in terms of states, but I am talking in terms of outputs. The output will be 1 clock shifted as far as the Moore is concerned with respect to the Mealy. The reason is very clear, because the output is going to appear only after the state transition is performed, whereas in case of the Mealy, the output appears as soon as the input changes. The input and the state defines the output, whereas the, so in this case, because the state transition is going to be delayed till the next clock, the output is not going to appear. So, first output I have to ignore. So, the two machines are equivalent in the sense that the output from the Moore is 1 clock delayed from the Mealy. So, if I am ready to take this definition of equivalence of machines between Mealy and Moore, then I can say that this particular machine is equivalent to this. The outputs are going to be the same. Of course, the fact that here I have shown exactly 1 clock is somewhat related to when actually the inputs come. The inputs may actually be changing, not just synchronized with this, it may be synchronized, but it may be appearing just before. If all the changes are sensed just before the clock, then the difference is going to be marginal. It will not be, they will not really be shifted by 1 clock period, but they will only be marginally shifted, because it actually depends on when the input changes occur. But considering that the input changes are synchronized and this input change is going to be only sensed by this particular clock, this is what I am going to get. So, I am going to get 1 clock shifted from, in case of the Moore, vis-a-vis the Mealy machine. Let me take another simple example just to show the fact that how the state splitting occurs. So, let me take another, let us say these are 3 states. This is, let us say, let me consider this particular state diagram. So, now I have, if I consider state as 0, I have only 1 incident edge on it, and so because there is only 1 incident edge, let me call it A. So, S0 corresponds to state A here, and output that I will associate, I will take the output from this, so output will be 0. If I look at state S1, S1 has 1 incident edge this one and another incident edge this one, and with this I have an output of 1 and I have an output of 0 here. So, I have to split. So, I will split into, let us say, 2 states. Let me call it B, okay, let me call it B0 and B1, and output, let us say I associate 0 and 1 with this. So, now I have S1 is getting split into 2 states, B0 and B1. Consider S2, S2 has 2 incident edges, this one and this one, output is 0 and 1. So, again let me split it into C0 and C1. So, I have now 5 states, instead of 3 states I have 5 states over here. issue is how do I complete my diagram. So now let us look at state S0 and consider all the edges that are going from state S0. If I consider this state S0, this particular transition, so of course there is only one state corresponding to this. So this is a transition which takes an input of 0 and goes to and produces an output of 1. And now because I am producing output of 1, but this particular state S1 is being split into B0 and B1. So I have to choose the particular state which actually produces an output of 1, and in this case this is the one which produces an output of 1. We look at this particular edge, the outgoing edge from S0. So this is one produces an output of 0. So I will actually now let me come to S1 and we come to B0 0. Now if I consider the outgoing edges from this, the outgoing edges from this are two edges. This one goes to state S0 and it produces output of 0. So it does not matter here, I will consider this and this, both of them will go, because they are both equivalent to, they are all split from S1. So I have to draw both these edges corresponding to just one edge over here. This particular edge will translate to these two edges. Now when it comes to this, things are little more complex. 0 1, because I have to, when with this particular two states, but output is 1, so I have to go to this. I will go to this particular state which is 0 1. Now let us consider this state S2. S2 I go to don't care, this is don't care, I go to S1, but now S1 is B0 and B1, but this is 0 state, so I will don't care I should of course make sure that all the transitions are specified at each state, for all the input combinations I should have a transition specified, then only it is a deterministic thing, and that I have all the transitions specified, uniquely specified. So I have checked both C0, C1, B0, B1 and A and these 5 states, and this is an equivalent Moore machine, and it is not very easy, very difficult to just draw the timing diagram and make sure that the delay, this is just delayed, the output is delayed by 1 clock cycle over this, because the way we have performed the transformations ensures that. Let us look at the other problem that is a little more difficult to directly see. The splitting is very easy from Mealy to Moore, but if you want to transform from Moore to Mealy, so I have this particular Moore machine and I need to transform this Moore machine into a Mealy machine. So what will happen in the Mealy machine is basically the outputs will be pre-pawned, isn't it? Like in Moore machine, when you are going from Mealy to Moore, the outputs are getting post-pawned, because now what is going to happen is the outputs that are going to be associated with the destination edge, that let us where you are incident. So this particular output is going to get moved to this. This particular output is going to get moved to this. So now in the Mealy model, the outputs will go to the edges rather than the states. So which are the states which can merge actually? So because anyway the outputs are not really of significance. What is of significance here? Because outputs associated with the states are not of significance, because they are anyway going to be merged into the transitions. They are going to move to the transitions. What is important is, are there states for the same input, they are going to the same state, next state. If I now consider all the states, so let us say if we consider this, if I consider A and B, A, if let us say consider a machine which is in state A, if I apply 0 it is going to B, but if I apply 0 over here it is coming back to A. So they are not going to the same state. If I consider A and C, if I apply a 0, A goes to B, but C goes to D. But if I now consider, so they are going to different states, but if I now consider the pair AD, if I apply 0 input, it goes to B and D also goes to B. Similarly, if I apply 1 input, A goes to C and D also goes to C. So AD is a candidate for merging, and I can merge these states AD and generate another state diagram like this. Of course, I have to consider all such possibilities where the next states are the same. So if you draw the state table, it will be, from that it's easy to judge the which states are going to the same next states for the same input combination, for all input combination. So AD is now the same, but now let me see how I am drawing this. So I have merged A and D into one state called AD in the, okay, previously I was giving different names, I have given the same name here. So let me just differentiate by calling them B dash C dash AD dash. Okay, so now if I look at it, so AD has been merged into one state called AD dash, and what we have here is, if I have a 0 input, I am going to go into the state B dash. What will be the output associated with it? Output that was associated with state B will be moved to this particular edge. The output was 1 and that has been moved to this particular edge. Similarly, when I am applying 1, I was going to state C, but because both were going to state C, and after all there is going to be only one output associated with state C, there is not going to be any, there is no problem of consistency here, because both these are going to the same state and the output was associated with the state, and that has to be a unique output, so that will get moved to 0. So this particular edge will become 1 0. So now as far as, so I merge this. Now what happens to this? When C was going to D with 0, but D was having an output 1 and A was having an output 0. But it is not a problem, because any edge which was terminating in D before will have an output 1. Like C to D edge was this particular transition, the output is 1. Whereas this this transition, B to A transition, the output will be 0, because anyway I am going to move the outputs to the transition and not associate with the states. So though these states which are got merged into Mealy into one particular state, though they have different outputs associated, but that's not of consequence. What is of consequence is what the next states were. So in this manner, it's simple to transform Moore to Mealy and Mealy to Moore, but with the restriction that we have seen in terms of timing. So with this, it's what we have seen is, we can finally, when we talk of realization, we will see the realization of these two, and we can see that we can easily, if we given a problem and if I find that the other realization is going to be simpler, I can just choose the other realization. So now let me talk about, so if you consider the problem, what was the problem? The problem was, the realization problem was, given the state machine, I have a set of inputs. This is my state register. This is nothing but some combinational logic. This is X input, this is Y, this is next state, and this is present state, and this is clock. So I have two problems here. The problem of synthesizing, so this is the general structure for a Mealy model. I can do the similar one for the Moore model, because in case of a Moore model, what happens is this logic gets split. The next state function is what we have here and the output function is what we have here. But no, that's a fairly trivial thing. Right now I am not discussing that. So let's consider this. So in this case, I have two problems here, synthesizing this and synthesizing this. And once I do that, I would have realized my state machine. Now let's talk about how do I synthesize my state register. Synthesis of the state register is nothing but, what is a state register? State register is nothing but a set of flip-flops with a common clock and inputs and outputs. So you all studied about flip-flops, so we will not spend much time talking about flip-flops. So let me just very quickly review the flip-flops that you have studied before. SR flip-flops, JK flip-flops, D flip-flops and T flip-flops. These are typically the 4 types of flip-flops that are used. SR flip-flops are the simplest, and you can simply realize them by putting 2 NANDs back to back. What happens in an SR flip-flop is the set input and reset input, except that there is one restriction, that both these inputs should not be 0. Sorry, both these inputs should not be 1. You should not activate both these inputs together. So either S has to be 0 or R has to be 0. Now let's look at this. These are called the characteristic equation of a flip-flop. any flip flop that you take, we write a characteristic equation, and if you look at this characteristic equation, one thing about it, though it looks like a typical Boolean equation, all these variables are Boolean, except that we have this time and we have this t plus 1. And the notion of t plus 1 is complete only in the framework of a clock. It is a clock which transforms t to t plus 1. So this is what is going to happen in the next clock. So the assumption is that there is a clock which is not specified anywhere in this equation, and it is that clock which is going to define this discretization, that is t to t plus 1. And once these equations are written many times, one ignores writing this t. You can just write qt plus 1 r dash q plus s, implying that wherever you are not put, it is corresponding to the current time, and when you are writing t plus 1, you are referring to the next clock period. So we have 4 equations over here. If you want to analyze any one of them, we can do it. This is the simplest one of them, the D flip flop, which does nothing but does the delay. It takes the present input and puts it as an output in the next time clock. Q does not come here, only the D comes, dt is qt plus 1. If you consider T flip flop, this is also very commonly used for implementing certain type of circuits. Later on we will see. What it does is, if T is 1, it toggles the input, so it is called the toggle flip flop, that is why the name T comes from. And if T is 1, qt plus 1 is q complement t, that means it will toggle it. If t is 0, it preserves the input, so qt plus 1 is nothing but qt. These are the characteristic equations, and they are the fundamental way of describing these flip flops, because they will be useful for doing my synthesis. JK and SR flip flops have 2 inputs, D and T have only 1 input, apart from the clock input. Clock input is implicit in all of these flip flops. So once we have what is called this characteristic equation, then we go ahead and have what is called an excitation table. I am drawing an excitation table for the T flip flop. You can draw the excitation table like this for any of the other flip flops. What does excitation table do? If I go back to this diagram, I have to make a transition from the present state to the next state. So I have to generate my next state, and this next state will become next state over here. But I am not implementing, if I am just implementing it a set of D flip flops, my next state will be nothing but, this output will be nothing but the next state itself. But when I am having any other type of flip flop, what I have to generate is not the next state, but I have to generate the inputs required by which this particular state register will go to the next state. After all, what I want is, in the next clock period, I want to go to the next state. But whatever are the inputs required, the excitation inputs required for this particular set of registers to go to the next state is what is required. And so in that case, I will directly not generate the next state, but generate the excitation inputs. So what this excitation table shows is, for any type of a flip flop, how can I go from each of the present state to the next state? That is, if qt is 0 and qt plus 1 is 0, what is the input required to go from qt to qt plus 1? So if I am going from 0 to 0, this is for a T flip flop, one can draw this for a D flip flop, or for a JK flip flop. JK will have 2 columns over here, or SR flip flop, again there will be 2 columns. So going from 0 to 0, I require a T of 0, 0 to 1 I require a T of 1, 1 to 0 I require a T of 1, 1 to 1 I require a T of 0. Toggle input. So this is the input that is required for making a transition from this to this. So once I have this, I am ready to do my synthesis, I am ready to go to the next phase of my design. So let us see how do you proceed. So the first problem in state machine realization is the problem of state encoding. I am taking the same example that I had before. This was that Moore machine which was reduced to a Mealy machine. So of course one can take any other example. So I have this 3 states over here. So my first problem is, how do I encode these states? what type of binary strings or binary representation I represent these states from. After all, finally everything has to be translated into some binary representation. So I have given you one state encoding over here. One can choose this or any other encoding that one likes. Later we will talk about some encodings may give you better, let us say, results. Better results means more compact realizations than others. So in this case I have AD00, B01, C10. This type of an encoding I already discussed. This type of an encoding is called minimal encoding. For 3 states I am only using 2 bits. I could have done a one hot encoding. A one hot encoding could have been 001, 010 and 100. So this would have required 3 bits because there are 3 states, but let me go ahead with this. So this is one type of an encoding. So this is the first thing that I do. Once I have this encoding, then I can translate this diagram into a table like this. If you consider this table is nothing but the representation of this particular diagram. Also, along with the fact that the decision that I have made is, I have made a decision that I will use T flip-flops to implement the state register. The state register, if I decided the T flip-flops to implement the state register and I had chosen a 2-bit encoding, minimal encoding which is 2 bits, so that means I will require 2 flip-flops to implement my state register. And the 2 flip-flops will require 2 inputs, T1 and T2. So in this case, the state that is coming out of them is Q2 and Q1, and what I require is T2 and T1. So what it is showing you is, it is basically a state transition table, just like you have the state transition diagram. If I am in present state 00, present state 00 is nothing but AD, and I have an input 0, I go to B. So what this translates into a row over here. Each of the edges will translate into a row in this table, 0, 0, 0. The next state is 0, 1. To go from 0, 0 to 0, 1, I will use the excitation table that I had discussed before. Write down what are the inputs required. So T2 has to be 0 because 0 to 0. T1 has to be 1 because I am going from 0 to 1 and I need to toggle. And the output that is associated is of course shown to be 1, that was coming from that edge that we discussed. So if you consider any other edge, I will have a similar, let us consider this particular edge. When I am going from B to AD, I do not care what the input is, output is going to be 0. So B is 0, 1 in my encoding, this corresponds to A, this corresponds to A, this corresponds to B, this corresponds to C. 0, 1, input that I receive, okay, this is X and this is don't care, please don't confuse, okay, this is actually X input and this is don't care. So I get a don't care input, and for the don't care input I go to the next state 0, 0, but to go to 0, 0, from 0, 1 to 0, 0, I require 0, 1 because T2 doesn't not be toggled, but T1 has to be toggled, so I require and my output is 0, that was the edge associated with it. Similarly, for example, to go from 1, 0 to 0, 1, for the input 1 when I am going from C to B, this corresponds to B, the edge going from C to B, I require to toggle both of them, so I require 1, 1. Because 1 is to go to 0, 0 is going to 1. Output was 1, that comes from the edge that was given. So I have this input, column for the input, column for the present state, column for the next state. Present state to next state, I have this particular column which is the excitation input. Excitation is nothing but look at the excitation table and see how can I make these particular transitions. How can I make a 0 to 0 transition, what is the input required, 1 to 0, what is the input required. So for each case I can write down the entries for this column by looking at this and what are the inputs required for going from, for each of the flip-flops to go from here to here. And now once I have generated this column, now my problem is fairly straightforward. I have already designed my state register, which was nothing but the set of 2 T flip-flops. The only thing now I have to do is I have to design my combination logic. And what is the combination logic that I need? I need a specification of this combination logic, and the specification of this combination logic is nothing but you remove this. You remove this particular column, treat this as an input for a combinational circuit, and treat this as the 3 outputs that you need from the combination logic. So they are the 3 inputs and they are the 3 outputs, and you can use any of the minimization techniques that we have discussed before, Carnot map or Quine-McCluskey, and generate the circuit that is required for generating these outputs. There are, of course, because of the fact that I had 2 bits, there is something missing here. The encoding 1 1 is missing. So what do we do with 1 1? I can take it as don't care, because that will help me to minimize the circuit. So I can once design the combination logic, and so that my job of realizing the state machine is over. I already designed my flip-flops, the state register, and I also realize my combination logic from this, and I will get the required circuit. Let me just go over the steps that we followed. The first step is the step when we convert the description into state machine. That is the first thing that we need to do, because you have given a description, an English language description of a problem, let us say a pattern matching problem. I have to convert it into a state machine. Minimize the state machine. I already have studied how can I find equivalent states which are redundant, and I can replace those equivalent states by a single state. So I can perform that minimization to get the minimal number of states. I encode the states. This is the step at which we decide that what is the binary string that is going to represent each of the states. Choose a set of flip-flops for state register. I have to decide which type of flip-flops I am going to use for implementing the state register, and of course it is not necessary that I have to use the same type of flip-flops. If there are a few problems where it may even be, we will talk about those later, when the problem is such that maybe at one place a set of T flip-flops is better, and for some other places D flip-flops is better. Typically when you are choosing a set of flip-flops, unless you can find out something very specific in the problem, the simplest thing is to go ahead with the D flip-flops, because in case of D flip-flops this particular step gets avoided. Use the excitation table to arrive at the specification of the combination logic. This particular part gets avoided because the inputs required are nothing but the next state itself, because Qt plus 1 is nothing but dt. So there is really no extra effort required in looking at the excitation table and getting the inputs. So this is the last stage is of course synthesize the combination logic, and this we follow the typical methods that we have already discussed. So now, but this is a problem which is a fairly straightforward method of synthesizing the state machine, but we should also realize that doing this completely in an, let us say, in a brute force method, like without really thinking about the problem, what are the pitfalls that can occur? Of course you will realize it, you will get a state machine which, you will get a circuit which actually replicates, or it actually implements the description, the state machine that you have drawn. Of course whether it meets the specification, whether it meets the language description or not is something beyond this, because many times the problem is in actually getting the proper state machine, because rest of it today the tools are available and you can just use push button technology, just synthesize the circuit for realizing a given state machine. One of the problems where the steps, let us say, if you look at it, a step that is a key step which can have a lot of implication on what you do later on is encode the states. The way you encode the states has an implication on the complexity of the logic. On one hand, if you encode it with, let us say, minimal encoding, you are ensuring that the number of flip-flops that you are using is small, but you do not know what is going to be the impact of this on the logic that is generated for realizing the next state, the state transitions. because it may happen that one hot encoding which actually has more number of flip flops might be much simpler in terms of the combination logic that is required to implement the state transitions. So, the trade off here could be between the flip flops and the logic, and there are methods by which one actually can see whether, of course one method is to do both the designs and see whichever is cheaper, but on the other hand there are also techniques by which you can do a little bit of a look ahead, whether you can do some evaluation or estimation. We are not going to talk about that in this course, but there are methods to do that. Similarly with the flip flops, but as I said, typically you use D flip flops, but if there are a lot of transitions which are counter type transitions, transitions which require mainly toggling. Of course, this means that you already encoded the states, because that is a so let us say most of the time most of your bits do not change, but if at all they change, they just toggle. It is like the counter type of a situation, then you try to use T flip flops, otherwise by and large one uses D flip flops. These steps are of course very routine and involves the minimization. So with this we will stop now. If there are any questions we can take up.